Welcome back to another video. In this one, we're going to look at how those different orbitals that we made actually overlap, the different types of overlap we can have that form bonds. Right, now, in those other videos, we talked about the importance of hybridization, how we went from s and p orbitals to sp orbitals, sp2 orbitals, sp3 orbitals, etc. And how this kind of told us where we have 2 orbitals, 3 orbitals, or 4 orbitals to accommodate electron geometries. Now, when we're talking specifically about bonds, there's going to be 2 different ways that we can have these orbitals overlap so that they can share electron density. All right, now the first and most efficient way, the way that gives us the most overlap, is what we call a sigma bond, which gets the small Greek sigma as its symbol. Now, sigma is going to be an end-to-end overlap. So that's what's going to give us so much space. Right? We see that between our s orbitals, between our s and our p orbital, and between our p orbitals. We have this area where both orbitals exist, and so both electron densities exist, and they get to get shared with those neighboring nuclei. Right, so another way you can think about this is head-to-head overlap. And this is one of my favorite phrases in Gen Chem, to be honest. There's a cylindrical symmetry of electron density about the internuclear axis. If you want to just sort of impress your family or friends at some random dinner, you can just they say, hey, what are you learning about? Oh, we learned about how bonds are really the first bond really focuses on creating a cylindrical symmetry of the electron density about the internuclear axis, and they'll look at you like, wait, what? That's a whole bunch of like $5 words there. But really all it means is that if I've got nucleus 1 and I've got nucleus 2 over here, and I want to share electron density with both of them, where am I going to put the electrons? We're going to put them in the middle so that the distance between these electrons is as short as possible between the 2 nuclei at any particular time. All right, so you can kind of imagine that I've got this cylinder, right? Because again, we're really going to be in 3 dimensions, where these electrons want to exist to form that first bond. Right, my electrons all exist in here between these 2 nuclei. Right, and that's what the sigma bond is going to give us. It's going to give us a fairly large amount of overlap so that the electrons get to be close to both nuclei. Now we do run into a problem, however. And the problem is that once I take these 2 nuclei and I put that cylinder in between them with my first pair of electrons, that area is full. Right? I've used up this space. Well, what happens when I want to share more than one pair of electrons? We've talked about systems that have multiple bonds. We need to have another place to share. And the way that we're going to do that is going to be above and below the nucleus. And this is going to be done with pi bonds. So we have unhybridized p orbitals here. Right? Actually, we only have 2. Let me only draw two arrows here. Right? One p, we'll call it p1 and p2. And they have this sort of side-to-side overlap. And I don't love this particular depiction of it. It uses those very dumbbell-shaped p orbitals to form the pi bond. And it makes it look like there's a whole lot of overlap. This actually works better if we take that more sort of split s orbital that p orbitals actually resemble a little bit more. And we say, okay, here's p orbital number 1 with my node and my nucleus in the middle. And here's p orbital number 2. With my nucleus in the middle. Now, see here, my area of overlap is actually very small compared to the overall area of the orbital itself, right? So the overlap area is fairly tiny. In comparison to, say, taking 2 s orbitals, right, we'll take one s orbital and we'll overlap it with this one, the percentage taken up by this overlap area is much greater with respect to the entirety of the s orbital, right? So more overlap percentage, shall we say, in a sigma bond than we see up here in the pi bond. So what does this mean? 1, it means that pi bonds are not as stable, typically, as a sigma bond, which means they are higher energy, which means that they form second. Or in other words, the first bond between any 2 nuclei is going to be a sigma bond. Any additional bonds beyond that are going to have to be pi bonds. So as an example of that, let's take a look at these 3 molecules. Here I've got molecular hydrogen. It's got one bond between the two hydrogens. So that's going to be one sigma bond. Now I've got ethylene sitting right here, C2H4. It's going to have one sigma bond, and it's going to have one pi bond. N2, molecular nitrogen, is going to have one sigma bond. I always like to think it's the one in the middle. And then it's got two pi bonds, right? The bottom and the top. Multiple bonds are always formed by these p orbitals, these unhybridized p orbitals, which works out well, right? C2H4, right? I've got my carbon, my hydrogens. What's my geometry here? It's trigonal planar. What's my hybridization? It's sp2. What's left over after I hybridize everything? Well, I've used up my s orbital on two of my p orbitals, and I have one extra p orbital. What does the p orbital do? The p orbital forms that pi bond. Excellent. Nitrogen, it's sp hybridized. It's got a 180-degree bond angle between this lone pair sitting over here and the bond. There's 180 degrees between those two. What's left over after I take one s and one p orbital? I've got two p orbitals left. Two p orbitals means two pi bonds is what we see in this molecule. Let's take a look at this visually. Here is formaldehyde. Now, formaldehyde is going to have a single bond, right, a sigma bond between the carbon and the oxygen, and then it's going to have the other bond that makes up the double bond, the pi bond. So what does this look like if we look at all the pieces? All right, let's zoom in on this for a second. Here's my carbon, and it's going to have some sp2 orbitals, right, and that gives it its 3 electron groups. That's going to give it its overall shape. And the second bond is going to be made with the p orbital between the oxygen and the carbon, right? This is my pi bond that happens above and below that internuclear axis, which is where we find our sigma bond. Now note that the pi bond looks like it has 2 lobes. Those 2 lobes are still one pi bond, right? 2 areas of overlap, right? This area in the middle, that makes up one pi bond because there's less % overlap there. Right? And we can see the sigma overlap here between the hydrogens and the carbon, and similar things going on over here with the lone pairs of the oxygen hanging out in their sp2 orbitals. All right, so there's sort of a diagram of how this all fits together. Let's look at another one. Here we're looking at acetylene. Now, acetylene is this molecule, C2H2, and it's going to have, that's a little messy, 2 carbons, 2 hydrogens, 1 sigma bond, and 2 pi bonds. So again, our first bond is going to form along that internuclear axis. 1 pi bond is going to happen above and below the plane of the molecule. 1 pi bond is going to happen in front and in back of the main line of the molecule. One of the things you can kind of see that we're setting up is now we have this second cylinder of electron density that coats this entire outside. So we've kind of made a cylinder around that interior cylinder that is the sigma bond. And that's really what these 2 pi bonds are going to do. They're going to form an outer layer around the inner layer, right? Another ring of electrons that still are between the 2 nuclei, just a little farther off center, right? I've got this interior one, and then I've got these electrons that are up here. And so they're still between the nuclei, but there's a little farther between them. So again, higher energy, a little less stable, forms second. All right, backing it up, let's look at something with all sigma bonds. Here we've got ethane. Ethane's going to be sp3 hybridized. I have the 4 electron groups, right? 4 electron domains that we're going to need because we have 4 bonds around each carbon. 3 to a hydrogen, 1 to the carbon. So each one gets to be what? sp3 hybridized, because I need 1, 2, 3, 4 orbitals. I have 1, 2, 3, 4 orbitals, sp3. All of the overlaps here are going to be sigma bonds. Right? Everything's going to be end-to-end. sp3, I've used up all my p orbitals. I can't make any pi bonds. We're done there. Right? So sp3, 4 bonds, all sigma. Ethylene, we looked at this a couple slides ago. Here's a prettier image of it. A couple different ways to view it. First of all, here, let's look at all the sigma bonds that exist. With those sp2 orbitals, we'll take out the pi bonds, we won't form them yet. We can see we have these two unhybridized p orbitals out here. But before we connect them, we can see that we've got this trigonal planar shape made up by those sigma bonds. The pi bond, right, as those two p orbitals come together, and here's the image that I really like of it, showing you how small an area there really is for the overlap of the pi bond, which we just sort of then abbreviate to give us these two big areas, which is what we see in all of our other images. It just kind of exists above and below, but there's very little area in the center where both electrons, one from each carbon, can kind of exist. And here's our depiction of it as a two-dimensional, or in this case actually still three-dimensional since we got it going back and forwards. We flipped it on its side so everything was on the plane of the page. That's what we'd be looking at. So again, here's our pi bonds that we see. Here's all of our sigma bonds. If we put them all together, it looks like what we saw on the previous slide. Last one we're going to look at, same pretty way, is we're going to bring it back to acetylene. And again, see that really big cylinder of electron density that's extending around that internuclear axis. Right? So we've got this second cylinder around that core that we see up here of the sigma bond. So sigma is in the center and the pi is on the outside. All right, so we got that second cylinder around it. If we look at sort of an electron density map of where we find all of these electrons, we can see that as we add more bonds, we get a higher and higher electron density in between our two atoms, right? More electrons means that there's more cushion between the nuclei, also more things for them to hang on to. So again, we're going to get shorter and shorter as we go from a single bond to a triple bond, right? As we looked at our bond order trend versus bond length. Right? More electron density in the center, shorter and shorter bonds. The nuclei here are closer together than they are over here. Right? Farther away for our carbon-carbon single bond, closer for our carbon-carbon triple bond. All right, and all because we have different places we can stick that. So that's going to be how our sigma bonds are going to function alongside pi bonds, which are going to be our second or our third bonds, in order to allow atoms to share multiple pairs of electrons. And now what we want to be able to do with this is we want to be able to look at a Lewis structure, and we want to be able to identify how many sigma bonds we have and how many pi bonds we have. So work on practices in that. We'll do a few examples, and we'll come back and check it out later. Bye-bye.